Garfield. Gabe is out in Norman, Oklahoma, and today's talk is entitled Hazardous Weather Testbed Results from the Experimental Warning Program in 2014. So as you all know, NOAA has a number of test beds and proving grounds scattered about the country involved with various phenomenological pursuits. The Hazardous Weather Testbed in Norman is focused on primarily severe weather, convective weather, but not limited to that. They have a long-standing program that's been operating as part of SBC and NSSL's endeavors, and today we're going to focus on the experimental warning program. So this is sort of like a wrap-up, if you will, or summary, because convective season is winding down, at least for most of the country. So we're going to hear from Gabe today on some of the things that took place, some of the things, the experiments that were held, and I'll look at perhaps some preliminary results coming out of the test bed that may be making their way to Weather Service operations at some point. So without further ado, I should mention again that format, for those of you new to the VLab Forum, is about 30 minutes of presentation, followed by 30 minutes roughly of Q&A. So we ask that you hold off your questions to the Q&A period. And finally, the entire session here is being recorded and will be uploaded to the VLab Forum website shortly after the conclusion of today's session. So, Gabe, are you there?
I'm here. Can you hear me?
Yes, we can. Take it away.
All right. Thanks, John. I appreciate that and the invite. As John mentioned, I am affiliated with the Hazardous Weather Testbed here in Norman, Oklahoma. In particular, my title is the Weather Service Liaison to the Hazardous Weather Testbed. And this year, I served as the Operations Coordinator for Experimental Warning Program activities. So let's get on to it here. The NOAA Hazardous Weather Testbed is a collaboration between forecasters, researchers, developers, trainers, and users. And we spend time evaluating observing platforms, numerical models, algorithms, products, and services. It is a facility located in Norman, Oklahoma, in particular at the Weather Center, but it is not just a facility. It is also an organization. It is comprised of 3 different groups, including the Experimental Forecast Program, the Experimental Warning Program, and the GOES-R Proving Ground. Experimental Forecast Program is similar to the Storm Prediction Center in that it is concerned with the prediction of hazardous weather events from a few hours to a week in advance, whereas the Experimental Warning Program is interested in the detection and prediction of hazardous weather events up to several hours in advance. The GOES-R Proving Ground, which involves satellite and lightning platforms, is interested in both time and space scales represented by the EFP and EWP. The HWT Experimental Warning Program has a mission of improving prediction of severe convective weather at the warning scale. So this would be around the time of an event out to 2 hours before the event happens. And since Norman has a large community of researchers, operational meteorologists, students, and industry, it really is optimally located to investigate these things. But we do serve all the National Weather Service weather forecast offices and center weather service units nationwide. So we consider the HWT a vital component to the research to operations and operations to research process. So what is tested? Well, in particular, new sensors. This would include radar, satellite, lightning, etc. Also, new applications and algorithms, multi-sensor integration, for example, GOES-R proxies, lightning jump, very short-term models, and finally, new methodologies. This would include best practices, new concepts, products, services, and finally, someday, maybe social science integration can be tested in the HWT as well. For EWP in 2014, we had 5 different experiments, separate experiments. The first experiment was the multi-radar, multi-sensor best practices experiment. This was conducted in over 2 weeks in April. The big experiment was conducted in May and June. Now, the big experiment has been renamed from the spring experiment, as it was known in previous iterations, because of possible confusion with other experiment names. Also, the probabilistic hazards information experiment was conducted at the same time in May and June. The hydrology experiment was conducted in July and August, and finally the Earth Network's Total Lightning Network experiment was conducted in July and August as well. Compare this with the experimental warning program in 2013. The big experiment then consisted of 18 forecasters over a period of 3 weeks. This year, however, by the numbers, we look at the total number of forecasters, which is 56, which is a factor of 3 increase from last year. In addition, the number of weeks of operation went from 3 to 11. So you can tell that we expanded operations considerably this year. Additionally, 4 broadcasters participated in the big experiment, which was considered a success by both forecasters and broadcasters, given the useful exchange of information between the 2 groups. Now, to start with, the multi-radar, multi-sensor best practices experiment, I want to go over what the MRMS system is. First of all, it's multi-radar. It's seamless, three-dimensional display of available WSR88D data. And it also integrates multiple sensors. That is, the objective blending of radar data with surface, upper air, lightning, satellite, rain gauge, and NWP environmental data. As an overview, there were tests for the MRMS system in 2009, 10, and 13 in the Hazardous Weather Testbed. The feedback from these experiments helped secure MRMS's acceptance of an official operational system for the NWS. These products will be displayable in AWIPS-2 starting in February of 2015. So some questions that the PIs for the multi-radar, multi-sensor best practices experiment wish to pose are as follows. What are the best MRMS products for warnings? What are the optimal AWIPS-2 procedures for hail, wind, and tornado? How does MRMS best integrate into traditional severe weather diagnosis? And finally, how does MRMS calibrate against traditional products? Additionally, there were some secret hypotheses. That is, that MRMS products may improve warning decision-making by improving warning polygon alignment and precision, less false alarm area, speeding up storm diagnosis and triage, improving lead time to first severe, and finally, improving analysis and cones of silence. These secret hypotheses were not readily available to forecasters before the experiment began and only were revealed at the end of each week. In terms of experimental design, the PIs conducted controlled experiments with up to 6 archived severe weather cases. There were 2 groups of evaluators in 2 separate HWT rooms. One group was considered a control group with no MRMS data. The second group was the experimental group, which had the MRMS data available to them. Some early MRMS results. First of all, in terms of ranking storms, this occurred much faster with MRMS. Forecasters were asked to rank a number of storms in a 30-minute period using, in one case, no MRMS data, and in another, the MRMS data. In the control case, on average, forecasters were able to identify 8 storms or rank 8 storms in the process in about 30 minutes. In the experimental case, this number increased by about 50%, up to 12 storms in 30 minutes. Also, it leads to a quick diagnosis of storms using MRMS data. Forecasters looked at the Donovan technique in 2 cases, which compares the height of the 50 dBz echo to the melting layer to assess storm severity. In the control group, this took 48 seconds in case 1 and 17 seconds in the experimental group. In the second case, the gains by the experimental group were not as great, but still significant compared to the control group. Now moving on to the big spring experiment. There were 3 different major experiments going on. One was the GOES-R PGLM project, which included several different products. In fact, the bulk of the products examined in the 2014 Big Spring experiment were in the GOES-R PGLM group. This would include satellite products and lightning products. Also, the Norman Warp, or the OU Warp, was also involved in the process. This was a high-resolution numerical model at 3-kilometer resolution. Another set of models was the variational lapse models. There were 3 of them in particular, one static CONUS model and 2 relocatable 1-kilometer grid spacing models. So new for the Big Spring experiment and 2014 is the probability of severe product, and this is basically just a statistical model that is meant to highlight at a moment's glance the storms that look most likely to be severe. It is comprised of many different inputs, and it's been shown to be potentially helpful for developing thunderstorms. Also, the overshooting top detection algorithm, which is a satellite algorithm that also does essentially the same thing as the probability of severe, in that it helps to indicate which thunderstorms are most severe. The variational lapse model, as I mentioned, there are 3 different models of this version. They are on-demand, 1-kilometer forecast being the highlight of that. Also, a multi-field trending tool, which looks at gridded output. That includes model, satellite, and radar output that can be put in a time series such that you can see how a particular quantity has trended over time. And finally, the GOES-R Rapid Scan satellite was available to us in May. This included 1-minute updates. First, we want to look at the WRF synthetic cloud and moisture imagery product. And on the left, you can see an example of the GOES-R satellite for a particular time and the forecast from a synthetic cloud and moisture imagery product based on the WRF ARW on the right side. And this, in concept, is intended to compare synthetic satellite imagery with actual satellite imagery to provide a method for NWP model performance evaluation. Realistic satellite bands using the model output allow forecasters to more easily identify features that may be important to the forecast. The results from the forecaster evaluation of the synthetic satellite show that if the synthetic satellite agrees with observation, it can raise confidence in the forecast, also vice versa. When the synthetic satellite is on track, it seems to predict areas of storm development quite well. Additionally, another product is the GOES-R Nearcast. This product is basically observed temperature and moisture fields advected by a trajectory model to forecast the future state of the atmosphere. In concept, it provides forecasters with decision support and situational awareness, particularly for the development and intensification or weakening of convection. And in terms of evaluation, PIs for this project wanted to know if there was any utility in determining where the environment will be more or less conducive to convective development and maintenance from the current time to the near future. In terms of forecaster evaluation, forecasters note that Nearcast predicted the area of convective instability quite well. Additionally, forecasters noted that the area of convective initiation was also forecast quite well, and it usually occurred on theta E gradients. Finally, the projections of that gradient location were fairly accurate. Next product was the University of Alabama Huntsville Convective Initiation product, also known as StatCast. And this was essentially a probability of convective initiation at any one given point. It highlights the areas in the 0 to 2 hour time frame where convective initiation is most likely. The evaluation involved testing to see if this increased the forecaster confidence and extended lead time to the initial convective development. In terms of the results, the forecasters noted that this did enhance situational awareness. It often indicated convective initiation before there were radar returns, so that was considered quite helpful. And it is considered close to ready for operations. The drawbacks are it's not quite as useful for nighttime operation when the algorithm switches to using IR. And in particular, the temporal frequency of IR is not great enough to really be able to be of much operational value. Also, forecasters did need to calibrate to every scenario, including different locations and forecast situations. Finally, it was also prone to false alarms, especially in the lower probability range. The solution for this, I think, would be then to perhaps increase the threshold, perhaps dynamically in the future. Also, the overshooting top detection product. In this product highlights overshooting tops such that a user can quickly spot them in animations of visible and infrared satellite imagery. And this might be especially valuable during busy warning situations. It tends to point out strengthening and weakening storms, at least in concept. So in terms of the evaluation, the principal investigators wish to know, is it useful, and does the appearance of an OT have anything to do with storm evolution? So the results of the forecaster evaluation showed that it did enhance situational awareness. And also, this would be particularly beneficial, according to some CWSU forecasters, just for helping them out in terms of all the products that they have to look at simultaneously. So in terms of the time that it takes to view this, it's helpful also for broadcasters who often tend to work by themselves. The next product was kind of similar in nature and concept, different product, but the probability of severe that we mentioned before. And this is sort of a different, sort of a hodgepodge of different things that go together. You can see in this image that it highlights several different properties of this particular outline, including mu, cape, and shear, and mesh, and it puts those things together to come up with a sort of a statistical probability that that particular storm might be severe. And the concept is that it could assist forecasters in severe weather situations by highlighting storms that are more or less likely to become severe in the future. In terms of evaluation, the PIs wish to evaluate it on its ability to increase forecaster confidence and skillfully extend lead time to severe hazards for National Weather Service warnings during low risk as well as high risk severe weather days. In terms of the forecaster evaluation, the results suggest that it worked best for hail. It didn't seem to work very well for tornado or for wind, but for hail it worked quite well. Also, the trends were quite accurate as storms building seemed to definitely undergo a higher probability with time. Also, the sampling tool tends to give a view into why certain probabilities exist. And the forecasters, some of the forecasters like this, as they have an ability to see what goes into the probabilities, whether radar contributes more or satellite or what have you. However, the product does tend to struggle with mature cells. When the storm's already going, it's somewhat difficult to really tell if it has an enhanced probability of severe weather. But it is very helpful in tipping the scale just after initiation. So this product was very much liked by most of the forecasters, and most forecasters noted that they see a high utility in this in the future. The broadcasters that worked with us, thought this would be particularly useful for them, as I mentioned before, because they tend to work by themselves during on-air situations. So this type of thing seems to be very helpful. Also, another product was the pseudo-geostationary lightning mapper. And this was basically the total lightning we looked at almost exclusively, which is a combination of cloud-to-ground plus intracloud. And in concept, this can be used to identify convection that may contain significant lightning, both cloud-to-ground and intracloud lightning, which possibly can be related to storm intensity. And in terms of the evaluation, the trends in total lightning and the relationship to storm evolution were evaluated along with relationships between total lightning magnitude and other fields. So from the forecaster evaluation standpoint, lightning jumps and flash density were considered valuable for situational awareness. Also, lightning jump detection highlights rapidly intensifying cells. So much as the probability of severe and some of the other products highlighted rapidly intensifying cells, the PGLM data seems to highlight those, especially given that a lot of the data is very temporally dense. 1 minute updates seem to be very, very helpful for determining when a storm is increasing in intensity. Lightning flashes and flash jump algorithms also were noted to indicate updraft health in at least a few cases. From an aviation perspective, i.e. from a Center Weather Service Unit standpoint, the lightning products enhance nowcasting and could possibly help determine flight patterns. From a broadcast perspective, all the products are useful for broadcast meteorologists working by themselves during severe weather operations, which was a point that was often highlighted by the broadcasters. Another product that was used during the experiment was the PGLM multi-field trending tool for AWIPS 2. And this is a product that is basically a time series of any gridded product, such that you can see where a storm is trending in terms of quantities. It was designed to identify trends in total lightning, in particular to help identify lightning jumps in advance of severe weather. But any gridded product, for example, model data, can be displayed. And it's not that seeing this past data in this way could possibly increase situation awareness. In terms of the evaluation, forecasters were asked to evaluate the effectiveness of this product on multiple issues. This included the timeliness for implementing the tool, the effectiveness of the generated time series, the ease of use, and the effectiveness of the tool on observations beyond the PGLM. In terms of the results, many of the forecasters note that this has tremendous promise for being able to use it, but it really took a lot of time to use the product. In particular, they have these little circles that they have to adjust in time, and that process had gotten better from last year's version, but this version's, though better and has improved some, is still a little bit tedious to use, especially in sort of high stress pressure warning operations. Another tool that was used was the variational lapse. This was 3 models, 2 removable 1 kilometer grids that are run hourly out to 3 hours, and the other was static, covered the continental United States at a 2.5 kilometer grid, and it was run hourly. Some of the products included in this particular system were composite reflectivity, CAPE, updraft helicity, storm relative helicity, and finally simulated IR brightness temp. In concept, the model may help forecasters identify the potential for convective development along boundaries, i.e. where is convective initiation expected to happen. Also, it's thought that perhaps in overlaying this model information, environmental data with radar reflectivity and velocity, that might help the forecaster to better determine the surrounding of a given storm. Also, the model forecast evolution in general might help forecasters better anticipate storm behavior and development later on. And the PIs wished to evaluate several things, including the temporal frequency, whether or not this was, the output was at a high enough temporal frequency or if it was too much, whether the model can resolve small-scale boundaries or not, and whether it's useful for short-term forecasts. The results from the forecaster evaluation suggest that the VLabs help to identify boundaries in the CAPE field. Also, the theta E from surface analysis was considered quite useful. The CAPE forecast was fairly accurate generally, which was helpful for determining which areas to expect robust convection. Finally, the high spatial resolution, that is the 1 kilometer spacing, depicted smaller scale features that were very intriguing to forecasters. Some drawbacks of this particular system was that the VLabs tended to overestimate composite reflectivity. This is not only a problem with this model, but with many high-resolution models. Also, surface obs sometimes were erroneous, and that affected output, including CAPE fields. So that was considered problematic. Also, the relocatable domain wasn't quite large enough to contain all of the severe weather on particular days. Fortunately, most of these drawbacks are definitely things that can be quickly and readily addressed. Finally, the Super Rapid Scan satellite was available to us in May. Forecasters evaluated it and said that they used it to observe key storm scale features that they would not have been able to identify without 1-minute updates. And as a result, this enhanced situational awareness for convection. And they reasoned that this could also enhance the detection of fog advection and dissipation, as well as lake effect snow bands. Now, this was only used for a very short period of time, so forecasters imagined that they could learn more about how to use this in terms of severe advection or severe convection, and that they might be able to identify features in the future that just aren't impossible to see without those 1-minute updates. So very promising there from them. Another project that was considered was the probabilistic hazards information experiment. And this centers around a new tool that addresses problems with the current warning polygons. That is, in particular, the warning warning forecasters have to worry about reissuing warnings downstream to areas. That is, you have a discrete polygon that just doesn't move along with the storm, so you're constantly having to update. Also, not everyone is equally probable to get the hazard in those warning polygons. And finally, some areas are warned that have no threat whatsoever. So the solution is these sort of continuous probabilities that move along with the storm and can be adjusted by the forecaster. Some experimental objectives for this particular experiment. First of all, with this new prototype fee tool, how did forecasters use that system? Also wanted to conduct an experiment using continuous probabilistic threat objects with displaced real-time cases, i.e. these sort of canned cases. And then another objective is to compare standard warnings with the fee threat objects for canned severe hail events in terms of usability, mental workload, and weather situation awareness. Finally, they wish to collaborate with the experimental forecast program to incorporate their probabilities as background probabilities for the fee tool. So some early results from the fee experiment is that on-defense decisions are reduced significantly. And this is really because the fee tool allows for low probability hazard information to be communicated to the public. This results in richer and more detailed information for more storms. And the workload is really a non-issue when no more than 4 to 5 hazards are present or the storm is relatively well behaved. However, in the future, we'll probably need algorithms to provide first guesses to offset the workload, particularly for multi-mode events with complex evolution. So this can be a focus for future, and probably will be a focus for future testing and evaluation in the hazardous weather testbed. And it's a different way of thinking. That's another result. Forecasters are thinking more about the meteorology of the event as compared to the current warning system. So this enhances situational awareness. In the old system, or the current system, forecasters are more concerned about polygonology. That is, that they want to game the situation to make sure that they don't miss out on any events. This new system allows the forecasters to move away from that and be concerned more about the meteorology. And this will be a need for training in the future of exactly how to use this in the most optimal way. Another experiment is the hydrology experiment. Some objectives from this were to determine the skill of operational and experimental flash flood forecasting tools like FFG and RMS Flash Product Suite. Also to compare the watches and warnings the forecaster issued based on the experimental tools and compare to those that were issued operationally. Number 3, to determine the feasibility of issuing flash flood watches in the 0 to 6 hour time frame, which is similar to the time frame associated with severe and tornado watches. Finally, to assess the utility in assigning the probabilities, uncertainties, and magnitude to the experimental watches and warnings. And a couple early results from this experiment show that the flood watches and warnings, that is the experimental flood watches and warnings, were considered to be at least as good, or if not better, than the standard flood watches and warnings. This is sort of a subjective rating based upon the forecaster impressions. However, the flash flood watches and warnings, the results were a bit more mixed and suggest that more work may be necessary on this topic in the future. And the final experiment was the Earth Network's Total Lightning Network experiment. This was designed to test the warning utility of the ENTLN, Dangerous Thunderstorm Alerts. That is, whether or not they helped forecasters improve their warnings. It was a controlled experiment. That is, there was displaced real-time cases, or several canned cases that 3 forecasters a week would look at, and they would be evaluated by evaluators that come over and look at what they were doing and see why they were doing what they were doing, and then compare these warnings with in the situation with ENTLN data and those situations without that data. It turns out that the results for this are pending and could inform some decisions in the future. So with that, I'll go ahead and wrap it up and open up to questions.
Okay, thank you very much, Gabe. So the audience participating in the GoToMeeting, if you would use the raise your hand feature, we can unmute you and have you ask your question directly to Gabe. You can also use the chat function John, do we have anyone who wants to take the floor?
Sure. Joshua Sheck would like to ask the question.
Joshua, you're there?
Yeah, can you guys hear me?
Yes, we can. Go ahead.
All right. Gabe, thanks for the presentation. Very good. I'm wondering about the total lightning. Did forecasters have any comments? I guess I don't have any data to support it, but I wonder if being able to see exactly where the lightning is originating from, is there potential there to reduce polygon size or better identify the part of the storm with the potential for severity?
Yeah, to be honest with you, I'm not sure about the results from that. I was not only did I help coordinate that particular experiment, but I also participated as an observer. And from what I can tell, that there's a possibility of seeing aerial extent of severe lightning. But I think, as I can tell, there was a lot of focus still with forecasters on whether or not a storm was producing hail as opposed to lightning. So I'm not quite sure if that was helpful or not. But the results are still pending as the fact that it was just completed last month. So if you'd like, I can definitely get back with you on that.
Yeah, I just think it would be interesting to know what direction we're heading with providing the forecasters with total lightning. What are the end benefits that we anticipate based on the preliminary assessments? Thank you.
Yeah, definitely.
John, do we have another question?
Yes, Hong Li Yang wanted to make a comment regarding labs.
Hong Li, do you want to go ahead and make your comment regarding labs?
Yes, can you hear me?
Yes, we can.
I just want to clarify that on the CONUS labs run, it's not run hourly, it's every 15 minutes.
Okay, very good. Thank you for that clarification.
Okay.
John, do we have a?
That's all. Oh, I'm sorry. Tom Filiaggi, let me unmute him.
Tom Filiaggi, go ahead.
Can you guys hear me?
Barely.
Yeah.
Well, as you were talking about a lot of these conclusions, it seems to me that most, maybe even all, of these conclusions were kind of intuitive or expected. And so my question to you is, were there any surprises? Did we learn anything new, or did we just kind of get reinforcement of what we thought we already knew?
Yeah, that's a good question, Tom. As of yet, I have not seen any conclusions that seem off intuition, although admittedly, given that it's September, I'm sure that if there are non-intuitive conclusions, I'm sure that will be more embedded in the data. I would expect that there will be some non-intuitive conclusions, especially in terms of the lightning experiment and some of these other ones, perhaps even the fee experiment, as they really dig into the data, because there was a lot of work, I think, that was done on the sort of the frame of mind and the thinking that was involved in some of these decisions. So I'm looking forward to seeing that. Like you said, these things ostensibly enhance situation awareness, but especially with the controlled experiments, I think that those type of experiments are much more conducive for finding those sort of non-intuitive results.
Yeah, Gabe, go ahead, Tom. Tom, you're breaking up. It's bad connection there. No, we're gonna have to cut you off there. It's really choppy. So.
Jeff Craven has a question.
Jeff, go ahead.
Okay, it's an observation, and I realize there may be some political sensitivity, but I'm just going to pose it. We're struggling with consistency issues in the Weather Service in general, and we made a decision a while back to use the RTMA as an analysis of record, which I know is a slightly different thing, and there are other observation platforms like labs that we decided not to use. It puzzles me a little bit that we're continuing to see a lot of work on the LAPS in one aspect of NOAA and OAR, and yet we don't think LAPS is good enough to use as an analysis of record in another aspect. So I guess when we're competing for shrinking resources, what is your feel for whether we should or shouldn't be using LAPS, or should we be combining some of these analysis resources?
Well, that's a great question, and I think that really goes to, I guess, all of the models that are out there. We mentioned the Norman, WRF, obviously the LAPS. You know, you have the HER and some other models out there, and I'm sure there are other WFOs that are have their own version of things. I think there's probably, in my opinion, a call for really combining resources, especially now that the process for moving domains has become a lot easier. Different groups have figured a way to kind of have these floater domains, and that way it can optimize resources in terms of you know, getting much higher resolution forecasts and possibly even ensembles. So my hope would be that that results from the LAPS and other groups would really demonstrate the feasibility of doing this, and that perhaps that folks who have the ability to kind of bring things together would look to sort of crowdsource our ability to model.
Okay, thanks, Gabe. This is Steve Smith. So I've got a question on just sort of in this general observation area. So, you know, this is like a smorgasbord of lots of stuff, and it's great. And I understand the constraints and the way the HWT operates and the reason why there's, you know, all these things. But one question comes to mind, you know, almost all these evaluations showed that something, you know, helped improve situational awareness, but I scratch my head when I'm thinking about the fire hose problem, where, I mean, how can we throw more guidance things on at forecasters and, you know, increase the fire hose and yet also improve situational awareness? It seems contradictory to me.
Yeah, that's a great observation. Somebody else wants to comment on that? I heard something in the background. Yeah, as far as I understand it, yeah, that's going to be a big problem, is, you know, this increased fire hose of information. And I think my understanding of this sort of ad hoc, especially with the big experiment in particular, this sort of ad hoc approach is meant to see kind of what sticks, I guess, in terms of, I mean, if you could, for example, you look at overshooting top detection versus probability of severe product or something like that. You see that both products have sort of the same general goal. Looking at this past year's evaluations, you might say that one system may have been more preferred over another. And so, in my opinion, seeing what really sticks. I think there's sort of an engineering mindset as opposed to a scientific mindset in sort of the HWT, where, you know, in the big experiment, you're more sort of fine-tuning expectations, whereas some of these other experiments were more controlled. So yeah, I think that will be definitely the subject for something that would be in a more controlled experiment, because right now we're doing most of that work in this sort of engineering situation, whereas I think in the future, if we're going to really evaluate how forecasters respond to this fire hose of information, we need to have a very good controlled environment with you know, social scientists who can really speak into that process. And so I agree with you that I think that's probably the next step, and I think there's been more interest associated with the folks involved in the HWT to really invoke a lot of that into future projects. Unfortunately, there's not a whole lot of expertise on how to accomplish that, but I think that's within, you know, sort of the long-term goals, is to understand exactly how much is too much.
Right. So for part of one of the experiments, wasn't there a human factors person who was evaluating what the forecasters were doing?
Yeah, yeah. I mean, they're people with various amounts of experience doing these sort of things. But we definitely know with the ENTLN experiment in particular, we had several people who were involved in, or who are involved in sort of human factors testing, who were observers in the experiment. So not in a formal sense, but definitely in an informal sense. Some of that stuff is already being brought to bear. I know we've had experiments of that nature, sort of, I guess, what is it, the radar experiment, the phased array, the FAR experiment several years ago involved some of that as well.
Okay, thank you. John, do we have...
Sure. Ron Prisbalinski has a question for us.
Ron Prisbalinski, you want to go ahead?
Yeah, I got a question concerning, was there any, I'm getting feedback on my phone, I'm not sure what's going on. But anyway, was there any investigation of the azimuthal-shear algorithm in this experiment this past spring, or would that be happening in the future?
Yeah, not that I know of. Right, the platforms that I mentioned are the only ones that I know of. I suppose, what system, if you don't mind me asking, is that associated with?
With the ADD.
Oh, just with the ADD in general. No, we didn't really. A couple, years ago, we did involve what is known as the 3D bar experiment. It was involving sort of an analysis of azimuthal shear from the 3D bar analysis of radar, and that was actually fairly helpful, I think, in identifying, the intensity of some of these mesocyclones. The problem with that was, as with a lot of these products, to be honest, is that it wasn't calibrated. So forecasters weren't actually quite aware of what, vorticity threshold was associated with what kind of severe event.
Yeah, we had the WIDS 2 here for about 3 years, and we found some initial observations on where we found some of the values at certain threshold would spawn tornadoes within the range of 100 kilometers. Beyond 100 kilometers, we saw a lot more variability.
Yeah, I'm sorry, I didn't quite understand the last part of that. It's a little fuzzy. Did anyone else understand that?
Ron, are your comment finished, or did you have a follow-up question?
No, I was just a comment that we did use the WIDS 2 system here for 3 years, and like I said, we were getting data from other adjacent WSAVs, and we found out that the most valuable portion of the WIDS 2 of the azimuthal-shear algorithm was within 100 kilometers of the VLab itself.
Okay, thanks, Ron. We're going to move on. John, do we have another speaker question?
No additional questions.
Okay, let's see. I've got a question, follow-up question, Gabe, on the probability of severe. Is that coming out of the mirror system, or what's the source of that guidance?
Oh, that's a good question. Well, there's a group of guys at the University of Wisconsin, the Satellite SIMS group, or not SIMS group, but that same group of folks that have been developing this product over the last year. So as far as I understand, the guy who's heading that up, John Centennial, was involved, I believe, with the MIRRORS project at OU. So he was here for his master's degree. So he does have experience in that, but it's not, as I understand it, someone correct me if I'm wrong, but it's not directly associated with that particular project.
Okay, so, but the output is similar to what's envisioned for mirrors, I think. And I'm mentioning mirrors. We're actually going to have Kyle Ortega and Travis Smith give us a presentation on mirrors next month. But from my understanding is that's something what they're hoping to get out of mirrors is some sort of objective probabilities of tornadoes and severe weather and so forth.
Yes, yeah, and actually, I'm not completely aware, but I would hazard to guess that there will be some collaboration between the two groups, as John Centennial was actually a grad student working under Travis Smith. So I'm sure there will be some inter-dialogue going on there.
Okay, thank you.
Mm-hmm.
Other questions, John, from the audience?
Not at the moment.
Okay, I got another. Oh, go ahead, Dan.
I have one. Dennis Miller here.
Mhm.
From what you learned this year, do you have any preliminary thoughts about what you're going to be looking at next? What these test beds will examine next?
That's a good question. I think the big takeaway that I have, just preliminarily, is that the probabilistic hazards information tool will become, hopefully, a part of the big experiment. That is to say that we're actually going to, instead of looking at it more in a prototype mode, that we'll be looking at this and invoking this in a sort of a normal AWIPS2 environment. I think that's really the push of things, is to see this really implemented in a more natural operational environment. That's one thing. As regards the other things, I'm not quite sure. We'll be having a meeting shortly. That is the principal investigators here in town, and I will be having a meeting shortly discussing where to go next this year. The process of getting these things together, it takes a while, and usually by the time February and March roll around, there's very little room to really think of strategically about this. So I think this year, especially now that we are, next year, now that we are expanding operations so significantly, I think it will become more important to really strategize about how we will carry ahead in the future. But at least in terms of the fee tool, I see that as becoming a big part of the next experiment.
Okay. Did you say the V tool?
The fee tool, PHI, the probabilistic hazard information.
Okay.
Yeah.
Okay, thanks, Gabe. This is Steve Smith again. Another follow-up question on the MRMS control versus not control experiment. So you mentioned, you showed some statistics about the time it took people to rank storms versus in the two different experiments. So by that, this was you did like can cases where there was X number of storms, and you wanted them to rank subjectively the storms, and then one group did it with MRMS and one group did it without MRMS. Is that basically what you did?
Correct. As far as I understand it, yeah.
Okay. So the ranking, I mean, it surprised me a little bit because, I mean, there is in AWIPS, been there for a long time, based on the WDSS, the scan cell table. So I think, one can rank storms pretty quickly using that tabular thing. So anyway, I just point. And the other question I had on that, these control experiments, so the other was on the diagnosis. So the time it took to diagnose. So that by that, did you mean that the time it took for the forecaster to feel like they could decide to issue a warning or not issue a warning? That was the diagnosis phase, so to speak?
I think that is, and I'm not entirely sure, as I wasn't a PI on this case, but the way I interpret what I received is that the PIs asked the forecasters to use the Donovan technique at particular junctures and time them in the usage of it. And so it was one particular, technique that they were expected to use, and then they just simply timed them using sort of base standard data, and then in another case using the MRMS data. So I mean, I think to me, again, the result is a little bit intuitive. I mean, you would expect that would take a little bit less time with MRMS because in the Donovan technique, you're using the height of the 50 dBz reflectivity and comparing that to the freezing level, which may take a little bit of button pushing in the case of the standard data, whereas in MRMS it's in a single product. So I think that, I don't know if that result is anything more than what you would expect.
Okay. Okay, I got it. I got it. Thanks. It was within the context of the Donovan technique. One other follow-up I had is on the, I think this was for the fee experiment, where you mentioned this on the reduction in the number of on-the-fence decisions. So by implication, does that mean that the lead time on warnings would be less because people wouldn't be on the fence as long? Is that what that implies?
Well, I guess it would just depend on the situation. You know, I think I can imagine there's a time where there would be some delay in lead time, because I can imagine there's a case where a forecaster would be hesitant to issue a warning until they're very sure of something, and in another case that they might go ahead and issue the warning because they're concerned about missing something, right? So it would just depend on whether or not they were, you know, worried about missing something or not. For example, I would say, you know, if a forecaster were looking at a big town in the near future being impacted by a potentially tornadic supercell, they say, well, it doesn't look that great right now, but I'm going to go ahead and issue the tornado warning because I think that, you know, I don't know enough about this situation, and what if it ends up hitting this town, and I need to probably get some lead time on this. And maybe in the case of the P tool, you would hold off a little bit on that to update the probabilities, because on the meteorological standpoint, you would actually, you know, feel a bit less confident, if that makes sense. I don't know. It just depends on the situation.
Okay, fair enough. John, do we have any?
Yes, Steve Koch would like to ask a question. You may use it.
Go ahead, Steve Koch. You're on the air.
Yeah, Steve. This is Steve Koch. I have a bit of a cold. Can you hear me?
We can hear you.
Okay, that's great. I have a question about the process in the HWT for Gabe as to, you know, I hear a lot about a lot of products that are kind of directed towards the same problem. I'll give you two examples. One has to do with convection initiation, where storms may fire. There are at least 3, if not more, tools directed towards that. The variation of apps, the Lagrangian technique from Wisconsin, and the WRF from NSSL. Likewise, with identifying severity of storms, you've got a wide variety of techniques, including convective overshoots from satellite, as well as radar techniques and SATCAST, and just a lot of different things directed to that as well. So my question becomes the fire hose, going back to the fire hose, has any thought been given to doing a comparative value-added analysis of these different approaches, or you know, I looked at the hypotheses that you were testing, and lo and behold, the results were everything you looked at improved situational awareness. Someone else pointed that out. And that's because of the way that the hypotheses were set up. They were not rejectable, null hypotheses. They were hypotheses directed at what you expected to see as a positive outcome. So you really, you know, I'm not surprised that anything was rejected. So how are you going to deal with the rejection issue? How are you going to be able to address what's more important than everything else, and therefore deal with those?
Well, that's an excellent question, and I think, and honestly, in my observation of the EWP for the last 4 years, I've noted that is a particular weakness of things. It's not very scientific. You can't really, in the case of the big experiment, you can't really reject, like you said, the null hypothesis. And in a lot of these cases, they're set up in such a way that there's a lot of interaction between the forecasters and the PIs. And I think that's that particular design of that experiment. So the question is then, what do you do to actually add, you know, compare value added? And I think the answer is to do something very similar to what was done in the case of the MRMS best practices experiment, and more in particular ENTLN experiment, which was very controlled. So I think if you're going to look at value added, you need to have a controlled experiment where one group is using one platform and another group is using another platform, or still another. And I think in that way we can actually start to really recognize these things. So I think for the future of the HWT, in particular the EWP, we will need to really, I think, look at our overall strategy as moving more from just sort of the hodgepodge engineering approach to really being more strategic and looking at crowdsourcing some of these techniques such that groups that are sort of disparate are working with each other, and we're looking at which techniques and among those techniques are actually best at doing the purposes for which they were designed.
Yeah, I agree that looking at a controlled experiment approach that's identical to a data denial experiment. You've got MRMS, or you don't have MRMS, for example. That's a data denial thing. But I guess if you could apply that same approach to looking at different systems, together and looking at the value added of the different components, then you might be able to get an assessment of the value added in a relative sense.
Yeah, so in other words, a controlled group, but with other groups looking at various platforms.
Yes.
Okay. Yeah, absolutely. That's a fantastic way of doing it. Only limitation, obviously, would be space in the HWT. We'd probably only be able to do, probably up to 3 control groups given the design of the actual physical space, unless we figured a way to optimize the building for more platforms. But yeah, that's an excellent suggestion.
Very good. Thanks, Dr. Koch. And did you have any other questions? Oh, you muted. Okay, very good.
Back off.
I do not.
Okay, thanks, Steve. Anyone else, John?
Yes, Brian Mata would like to ask a question.
Brian Mata, you have the floor. Go ahead.
Yeah, hi, can you hear me?
Yes.
Okay,
Yes.
good. Yeah, Gabe, if you could comment on the apparent difference in the results between the hazardous weather testbed evaluation of the, I think you called it the trend analysis tool, versus the OPG evaluation of the same tool during the same week?
I actually can't comment because I wasn't aware of the other test, but I can tell you that at least as far as, I hope it didn't seem too negative on the tool, because as far as I understand it, the forecasters really like the idea of a time series, being able to compare things, or to compare a particular product to time. The tool itself was a bit clunky. There were various versions passed through and improved. I think we had over 20 different updates during the process of looking at this. And so in some cases, I think some weeks forecasters felt disinclined to using the tool as a result of their experiences early on. But as the experiment went on, I noticed that more forecasters were using the tool towards the end. And I think there was some definite positive feedback. And I think that it certainly, at least per the forecaster, seems to show good promise for the future.
Okay, well, I was just going to congratulate the testbed on not passing the tool in terms of, we just had this discussion about things that nothing ever fails in a testbed, but I would consider that one where we do have the conclusion is to reject. Is that correct?
I think right now, given its current state, I would say yes. I think the design of the tool is such that right now, or the way it was presented was such that I don't think that an honest evaluation of the product could occur. If it were reintroduced with some of the bugs removed and some of the suggestions implemented, then maybe some honest evaluation of that tool could improve its state. However, it's hard to say whether or not even those would be acceptable to the forecasters. But definitely, given its current state, I would say a solid rejection.
Okay, thanks.
This is Steve Smith. I got to jump in here because Brian raises an excellent point here. That tool was tested in the OPG by Kim Runk and the group there. They brought in forecasters there. They got a totally different result. So I'm not saying one is right, one is wrong, but it does raise the question about if you're testing, maybe we do need to test these tools in different test beds and to get independent evaluation, since there's some subjectivity involved, et cetera. But I don't know. We don't have a process in place to say one test bed or another is the deciding factor here, but it's an interesting result, to say the least. John, do we have other questions?
No more questions at this point.
Hey, Steve, I do have one more question if we have time.
Sure. Go ahead, Brian.
Yeah, another question for Gabe. The 1 minute imagery, and you talked about the convective initiation, the UAH StatCast. You said in the briefing that the algorithm was not as good at night because the IR imagery was not as timely as during the day. Did I get that right?
I think so.
Okay, can you explain that a little more? Because the imagery should be at the same time interval, right?
Okay.
Whether it's
yeah,
visible or IR.
Okay, I could be mistaken. Then that was secondhand information that I grabbed from someone else. So if that's an error, I apologize. But my understanding was that maybe it was the resolutions in some way, either temporal or spatial, that was not as useful, and that was actually one of the points that a forecaster had made on what they call the tails from the test bed, and so I pulled that from that directly.
Okay, it's probably the loss of the visible data at night that changes the algorithm outputs. Okay, thanks.
Thank
All
you.
right. So we're at the top of the hour, a little bit past, so we're going to have to wrap this up here. I want to thank Gabe for the overview and congratulate the contingent. There's an army of people who work on getting this test bed up and running and carrying out those experiments. It's a lot of work, and a lot of Weather Service forecasters benefit tremendously from participating in that. I want to acknowledge OAR's efforts and SBC's efforts to make that happen. So it's an educational experience for anybody who gets out there. Encourage people to see if their folks can participate. Coming up in October, as I mentioned, we have a presentation on mirrors. Also coming out of Norman, that's Kyle Ortega and Travis Smith, and this is a key piece to the enabling of the facets program and the fee tool. So I encourage people to tune in for that as well. In November, we're going to hear from Chris Lancey about the Joint Hurricane Testbed and what they're up to. And then in December, we've got Tim Schneider is going to talk about the High Impact Weather Prediction Project. So put those things on your calendar if you're interested. And thanks, everyone. Signing off.